Hello there, and welcome. Tonight, we'll explore something that sounds impossible, that when you move, space itself moves with you. Every step, every breath, every orbit of a planet tugs gently at the fabric of the cosmos. You're not floating in space, you're floating on it, a vast, invisible ocean that bends, folds, and flows around everything that has ever existed. Tonight, we'll follow those ripples from the fall of an apple to the trembling of galaxies, to understand how the universe truly works. And while you're settling in, before your eyes grow too heavy, I'd love it if you gently tapped subscribe or pressed the little hype button YouTube recently added. It's a small click, but it helps keep these experiments and explorations orbiting out into the algorithm. You can also leave a comment telling me where you're listening from and what time it is in your corner of the night. It's oddly fascinating to see where people are, drifting off with us, scattered across the world like stars across the galaxy. Now take a deep breath, let your day drift away, and let's travel together into the quiet corners of the universe. For most of human history, gravity was thought of as an invisible hand pulling things toward the ground. It felt simple. You drop an apple, it falls. You jump, and the earth calls you home. Newton described this pull perfectly, his equations predicting every orbit, every fall, every motion, with such precision that for centuries it seemed the whole universe was written in his language. But even Newton, brilliant and careful, once admitted he did not know how gravity worked. That gravity should be innate, inherent, and essential to matter, he wrote, is to me so great an absurdity that I believe no man who has, in philosophical matters, a competent faculty of thinking can ever fall into it. Something was missing. 200 years later, a young patent clerk with a head full of thought experiments decided to look at the problem sideways. Albert Einstein imagined a world where gravity wasn't a force at all. What if, he thought, space itself could bend? What if the presence of matter didn't pull objects the way a magnet pulls metal, but instead curved the stage on which everything moved? And so came one of the most beautiful ideas in science, that mass tells space how to bend, and space tells mass how to move. It's a simple sentence that hides a dizzying truth. Imagine space not as emptiness, but as a kind of soft fabric stretched across the cosmos. When something massive sits upon it, a planet, a star, a black hole, it presses a dimple into that fabric. Smaller objects nearby aren't being pulled by invisible threads. They're simply following the curves. The moon doesn't orbit Earth because it's tugged by some unseen string. It glides effortlessly along the bend that Earth's mass creates in the geometry of spacetime. Einstein's vision replaced the pull with a path. Objects in motion simply keep moving in straight lines, but straight lines are no longer what we think they are. A straight line through curved space looks like an orbit, a fall, a dance around an unseen bowl. Gravity isn't something acting upon you. It's the shape of the world around you. If you could see these curves, you might notice how space dips gently beneath your feet, how it stretches slightly around mountains, how oceans rest within shallow gravitational hollows. Even your body, small as it seems, bends space by the tiniest fraction. Every atom adds a wrinkle. Every heartbeat leaves a whisper in the geometry of the universe. We are all sculptors of the very space we inhabit. On Earth, we barely notice the bending. The planet is vast, the curvature subtle, the distance is small. But near a star, or around a black hole, space becomes a liquid thing. Light itself curves, flowing like a stream around a stone. Time slows, stretched thin by the steepness of the descent. What we call weight is simply the feeling of resistance against that bend, the effort it takes to remain still on a tilted plane of reality. When you stand, you are not being pulled downward. You are trying not to slide along the curve that leads toward Earth's center. Your body's muscles counteract geometry. The floor beneath you exerts an upward force to keep you from following the natural path space-time has already drawn. It's not that gravity grabs you, it's that the universe keeps trying to let you fall. Think of the astronauts orbiting far above. They seem weightless, floating freely, but they're not outside gravity's reach. They're inside it completely, falling forever around Earth's curve. The only reason they don't hit the ground is that the ground curves away beneath them at the same rate they fall. They're passengers on the geometry, drifting along the natural flow of the planet's warped space. When Einstein first revealed this to the world, it sounded like poetry disguised as physics. Space and time woven together, matter shaping motion, motion shaping time. It took years for the proof to arrive. During a solar eclipse in 1919, astronomers watched the light of distant stars bend as it passed near the sun. The pattern of starlight shifted exactly as Einstein predicted. Reality itself had curved before human eyes. Since then, every test from orbiting satellites to collapsing stars has confirmed the same truth. Gravity is not a force in the ordinary sense. It is the bending of the cosmos around anything with mass or energy. The larger the mass, the deeper the curve. The deeper the curve, the slower time flows, the stronger the illusion of weight. It means that what we experience as heaviness is simply our attempt to move straight in a world that isn't flat. Even the path of your breath, the fall of a raindrop, the orbit of a comet, all of them are stories written by curvature. And so, when you drop an apple, it doesn't fall because Earth pulls it. It falls because the apple is following the simplest path through a curved universe, the straightest possible line in a geometry that refuses to be flat. It falls not down, but inward, tracing the shape of existence itself. In that quiet realization lies something both humbling and extraordinary, that the weight you feel isn't a force pressing you into the ground. It's the echo of space-time's shape, a whisper from the universe, reminding you that even standing still, you are leaning gently into the curve of reality. Light, in its purest form, always takes the simplest route. It doesn't think, doesn't choose, doesn't wander. It follows what's called a geodesic, the straightest possible path through the landscape it inhabits. But when that landscape bends, so too does light's journey. Space itself curves, and light, obedient to the geometry of the inclined universe, flows along the curve as if it were a river winding through invisible valleys. The illusion is that the beam bends. The truth is that the stage beneath it does. Imagine starlight leaving a galaxy billions of years ago, setting off through the cold dark, never slowing, never stopping. It travels through the intergalactic void, unbothered by time, until it encounters something immense, a cluster of galaxies, or perhaps a single one, swollen with dark matter. That mass, heavy beyond comprehension, presses a deep dimple into the cosmic fabric. The light doesn't notice the mass itself. It simply follows the new shape of space. It curves without resistance, tracing the contours of the invisible depression until it continues on its way, slightly shifted, slightly changed. From our point of view, far away and watching from within another gravitational basin, it looks as if the light has bent around the galaxy. Sometimes, if the alignment is perfect, we see a ring, a perfect circle of light called an Einstein ring, as if the universe were signing its own geometry. Other times, the distant galaxy appears duplicated or smeared across the sky, a cosmic mirage formed by gravity alone. These distortions aren't tricks of the eye, but the honest rendering of how the universe warps itself. Space bends, and the image bends with it. If you could drift beside one of these beams, you would never feel the curve. You'd float along what feels perfectly straight, even as distant observers see you following a wide cosmic arc. That's the heart of Einstein's insight, that motion through curved space feels natural, effortless, straight. It's only when we step back, mapping light's course across the sky, that we see its path as something astonishing. Light's obedience to geometry reveals the shape of the invisible. Astronomers use this bending like a lens, peering deeper into the universe than would otherwise be possible. When a massive cluster sits between us and a distant galaxy, it magnifies and distorts the light behind it, revealing worlds too faint to see directly. Through these gravitational lenses, we glimpse galaxies born only a few 100 million years after the Big Bang, their light stretched and warped across time. The universe uses its own mass as a telescope. This bending isn't limited to faraway galaxies. Even here, near Earth, the effect is small but constant. The sun's gravity curves the path of light that passes near its edge, causing starlight to shift just enough that we can measure it. During the eclipse of 1919, when the moon's shadow hid the sun's glare, astronomers captured photographs of stars near the sun's limb and found them displaced exactly as Einstein's equations predicted. In that moment, humanity saw space itself flex and light obey. It's strange to think that what we see of the universe is never quite where it truly is. Every star in the night sky is slightly displaced, its light bent by gravity along the way. Even the glow of sunrise and sunset is shaped by the curvature of air and space. Every image you've ever seen, every shimmer of starlight, every photograph from a telescope, every glint on the surface of a lake is a collaboration between light and the geometry it travels through. Sometimes, when you look up on a clear night, you're not seeing a star where it is now, but where it was long ago. Its light having taken the only possible path across the bent fabric of reality. Each photon, each tiny particle of light, carries a record of the universe's curves. In their travel, they reveal the unseen scaffolding of everything, the dips and folds, the warps and waves carved by mass and time. Even black holes, which let no light escape, owe their mystery to this same principle. Light near their edges is bent so sharply it can circle the void entirely, looping around before escaping to distant eyes. The result is a halo, the Y photon ring, a luminous echo of paths once straight, now trapped in endless curves. To gaze at such an image is to see light dancing on the rim of geometry's most extreme expression. Every beam of light, no matter how far it travels, follows the will of the universe's shape. Its path is a story written by curvature, a conversation between the smallest particle and the largest scale. And though it never wavers from the straightest route available, that route is anything but straight to us. It arcs, it loops, it bends not because light is weak, but because the world it travels through is alive with gravity's quiet sculpting hand. So when you look at the stars tonight, remember that the light reaching you is ancient, and its journey was anything but simple. It slid through valleys of invisible mass, skimmed the edges of galaxies, wove through the cosmic web like silk in the wind, and arrived here to the back of your eyes, to your mind, to this moment. The stars you see are not where they appear, but where space itself once guided them. You are looking not just into distance, but into the deep, curved architecture of reality. Imagine standing still, feeling the weight of the world beneath your feet, and realizing that the ground you trust is not as solid as it seems. Beneath you, beneath everyone, everywhere, is an ocean, not of water or stone, but of something stranger, spacetime itself, vast and invisible, flowing silently around you. You don't feel it because you are part of it, drifting on its currents the way a fish moves through the sea, unaware that it swims. The universe isn't a void, it's a medium, a living fabric that ripples and folds, stretching from here to the edges of the cosmos. For centuries, we called it space, as though it were an emptiness between things. But Einstein showed that it's not an absence, it's the thing itself. A flexible, dynamic ocean where energy and matter interact, where gravity is the motion of waves, and time is another dimension of its depth. When something massive stirs a collapsing star, a merging black hole, a cosmic dance of titans, the ocean shudders. It sends waves across the universe, carrying whispers of that movement through the vast, dark, like ripples spreading across an infinite sea. These are gravitational waves, the faintest vibrations of existence. They move not through space, but of space, altering the distances between points ever so slightly as they pass. When two black holes collide, they create a surge in this ocean so powerful that even billions of light years away, the wave can still be felt. Not by human skin, but by the most sensitive instruments we've ever built. Lasers stretching down long tunnels, measuring shifts smaller than the width of an atom. And when those detectors catch the pulse of the wave, it's like hearing the universe breathe for the first time. The first confirmed detection happened in 2015, though the event itself occurred more than 1 billion years earlier. Two black holes had spiraled together, twisting the ocean of space-time until they became one. The waves from their collision expanded outward in all directions, crossing the cosmos until they reached Earth. When they passed, space itself stretched and shrank minutely, rhythmically, like a heartbeat echoing through eternity. For a moment, the entire planet rose and fell within the current of that invisible sea. It's difficult to imagine something so immense, yet so gentle. These waves carry no sound, no light, no color. They simply reshape the very geometry of reality as they move. If you were somehow floating far out in intergalactic space, the wave would pass through you without harm. You wouldn't feel it, but every molecule in your body would drift infinitesimally closer together, then slightly apart, following the pulse of the cosmos. It is motion without motion, energy without substance, the quiet hum of gravity itself traveling at the speed of light. Space-time doesn't only ripple, it also flows. The expansion of the universe is part of that same motion, a great outward tide that began nearly 14 billion years ago and hasn't stopped since. Every distant galaxy is a buoy on that rising swell, carried outward not by velocity but by the stretching of the ocean itself. The farther away it drifts, the faster it seems to move, as though the water between us is deepening with time. It's not the galaxies that are fleeing, it's the space between them that grows. Sometimes it helps to imagine yourself floating above it all, looking down not on stars and planets, but on the invisible surface beneath them. You'd see vast currents where gravity gathers matter, pulling galaxies together like eddies forming in a stream. Between them stretch the great voids, silent expanses where the ocean is calm, where space hardly bends at all. The universe would look less like a frozen picture and more like a living tide, forever shifting, flowing, shimmering with invisible motion. Even the light that crosses it feels the texture of this ocean. As it travels through the stretching fabric of the cosmos, its wavelength grows longer, its color deepens. This is the redshift, the fading of light as it surfs across expanding space. The glow of the early universe, once fierce and blinding, now hums softly in microwaves, cooled by the long journey through the swelling sea of time. Every photon carries the signature of that drift, a story written in the rhythm of the ocean itself. And though we stand still, we're part of that movement. The planet beneath your feet rides a spiral wave around the sun, which drifts through the arm of the Milky Way, which itself sails across the local cluster, all of it afloat on an expanding tide of space-time. The motion is everywhere, and yet we call it stillness, because from within the current, we move together, and it feels like calm. But it isn't calm. Its motion so vast and even that we forget we're moving at all. The ocean beneath you is stretching, breathing, trembling with history. Every heartbeat you've ever had, every second that's ever passed, every star that's ever burned, all of it has taken place within that fluid fabric. And even when the last star goes dark, when light itself fades from the sky, the ocean will remain, vast and invisible, still rippling from echoes of collisions long forgotten. To stand here, now, is to float in something ancient and alive. You are not sitting on solid ground. You are resting on the surface of space-time, and every breath you take sends a ripple through eternity. time feels like the most constant thing we have. It moves forward, steady and impartial, carrying everything along with it. A heartbeat, a sunrise, the ticking of a clock. Each moment follows the next, with such precision that we built our understanding of the world upon its end. Rhythm. But time, like space, is not what it seems. It isn't rigid. It isn't universal. It bends, stretches, and folds in the presence of gravity, soft and fluid as the space it flows through. The stronger the gravity, the deeper the curve, and the slower time itself runs. Einstein's great revelation was not only that space can bend, but that time is woven into it inseparable, like two threads of the same fabric. Together they form spacetime, a single four-dimensional geometry that curves under the weight of mass and energy. When space dips, time dips with it. This means that in the presence of something massive, a planet, a star, a black hole, the flow of time itself changes. It doesn't stop, but it drifts at a slower rhythm, like a stream thickening as it runs through deeper water. Imagine two identical clocks, one resting high on a mountain, the other down at sea level. To the naked eye, they tick in perfect unison, but they don't. The clock at the summit runs slightly faster. The difference is so small that only atomic precision can reveal it, yet its real time flows more freely the farther it is from Earth's mass. At sea level, gravity presses harder, bending space-time more steeply, and in that gentle curve, seconds pass just a little more slowly. You don't feel it, but your life unfolds within that subtle drag. Every breath, every thought, every beat of your heart occurs at a pace set by the curvature of the world beneath you. The effect becomes profound, near something massive enough to twist the geometry almost beyond recognition. Near a neutron star or a black hole, time slows dramatically. If you could hover just above the event horizon, the edge where light itself cannot escape, you would see the universe above you racing forward. Stars would seem to age in fast motion. Galaxies would drift and evolve before your eyes. Meanwhile, to an outside observer, you would appear frozen, your seconds stretching into eternity. To you, everything would feel normal, your pulse steady, your thoughts calm, but the rest of time would slip past like a rushing tide. This is the soft geometry of time, the realization that duration itself is relative, shaped by the landscape of the universe. The deeper you fall into a gravitational well, the slower your clock runs compared to those who remain higher up. It's not that gravity is interfering with the mechanics of time, it's that time is part of gravity's structure. When space curves, time leans with it. Every moment is drawn into the same invisible flow. We live inside this curvature every second, though we rarely notice. When GPS satellites orbit above Earth, their clocks tick faster than ours do on the surface. If engineers didn't correct for that difference about 38 microseconds per day, your phone's navigation would drift miles off course. The satellites must account for both their speed through space, which slows time slightly, and their distance from Earth's mass, which speeds it up. Without Einstein's equations, every map and every flight path would unravel into chaos. The devices in our hands depend on the softness of time. It's strange to think that what you experience as now isn't universal. There is no single moment shared across the cosmos. Your present might already be another world's ancient past and another's distant future. Every observer carries their own timeline, molded by motion and gravity, stitched into the curved fabric around them. Time is not a ruler, but a rhythm, played differently in each corner of the universe. If you could step outside space-time and look at it whole, you'd see something astonishing, not a line of events, but a vast structure, folded and intertwined. Every heartbeat you've ever had would exist alongside every one you will ever have, layered like pages in a book. To you, they unfold in sequence, one after another. But in the geometry of the universe, They are all part of the same sculpture, carved into the curve of space-time itself. This fluidity makes time both fragile and eternal. It can slow, stretch, and warp, yet it never truly breaks. Even at the edges of black holes, where time grinds almost to a halt, its passage doesn't end. It simply becomes so drawn out that the rest of the universe leaves it behind. To fall toward a black hole is to move deeper into the slowest seconds that have ever existed, where each instant could last forever. And yet, even in the ordinary moments of your life, the ticking of a kitchen clock, the turning of earth beneath you, time is bending, subtly, invisibly. The seconds you live are not the same as those passing just a few thousand feet above you. The universe is quietly sculpting duration around every atom, every motion, every thought. So the next time you watch a second-hand move, remember that its rhythm is not fixed. It is being shaped by the planet beneath your feet, by the pull of the sun, by the gentle drag of the galaxy's mass. Every tick, every beat, is a compromise between motion and gravity, a whisper from the geometry of space-time itself. The clock is not counting something outside of you. It is echoing the shape of the universe you inhabit. When we picture falling, we think of something ending a descent, a surrender to gravity's pull. It's a word that suggests failure or fear. But in truth, the act of falling is one of the most fundamental motions in the universe. Everything that moves under gravity, from an apple dropping from a tree to the moon circling the earth, is falling. The only difference is whether it ever hits the ground. The miracle of orbit is that it never does. Astronauts floating high above Earth aren't weightless because gravity has let them go. They are weightless because gravity still holds them completely, and they are in a state of endless, graceful falling. When Newton imagined the motion of the moon, he pictured it like this: a cannon on a high mountain, firing a ball across the horizon. Fire it too softly, and the ball arcs down, hitting the ground nearby. Fire it faster, and it travels farther before falling. But fire it with exactly the right speed, and the curve of the earth falls away at the same rate the cannonball falls toward it. The result is a loop, a continuous fall that never ends, a dance between motion and gravity. That, he realized, is what the moon is doing. And centuries later, when rockets began to reach the edges of the atmosphere, humans joined that dance. The sensation of weightlessness isn't the absence of gravity, but the absence of resistance. On Earth, the ground stops you from following your natural trajectory through curved space. Your feet push back against the planet's pull, and your muscles register that push as weight. In orbit, there is no surface to resist you. You, your spacecraft, and everything inside it are falling together. Each object follows the same curve through space-time, so within that shared fall, all relative motion disappears. You drift, not because gravity is gone, but because you are in perfect harmony with it. Outside the window of the International Space Station, Earth glides silently below, vast and luminous, wrapped in ribbons of cloud. The station travels at nearly 5 miles per second, fast enough that as it falls toward the planet, the ground curves away just as quickly. The result is an eternal free fall 16 times around the world each day, tracing a smooth arc through the bent geometry of space. The astronauts inside eat, sleep, and float in that delicate balance, their bodies no longer feeling the press of gravity, though gravity is what keeps them there. It's a strange paradox. If you could somehow turn off Earth's gravity entirely, the station and everyone inside it would fly off in a straight line into the void. They would no longer orbit. They would simply leave. The curve that keeps them circling is not an obstacle to escape. It's the reason they remain. Spacetime's gentle dip around Earth guides them like a track guides a train. Except the track itself is invisible, made not of steel, but of geometry. This idea that orbit is a fall changes how we think about motion. It means that every planet around every star is in free fall. Every moon, every ring, every comet. The solar system isn't a set of objects spinning in defiance of gravity, but a collection of bodies surrendering to it completely, their inertia tuned so precisely that their falls wrap around endlessly. Even the sun itself is falling, drawn by the combined gravity of the planets and the motion of our galaxy through space. Everything falls, always, together. If you could see the trails these objects carve, you'd find a universe made of spirals and ellipses, a tapestry of motion shaped by attraction and speed. The grace of orbit isn't chaos, but the quiet order of falling done just right. The same principle keeps satellites in motion above Earth and keeps the Milky Way's stars from collapsing into its center. It's the same story, written in different scales, from an apple's brief descent to a planet's billion-year drift. Inside the station, an astronaut lets go of a droplet of water. It hovers, suspended, spinning slowly, reflecting her face back in miniature. Around her, tools and notebooks float like slow-moving thoughts. Every one of them is falling, tracing the same perfect path. Even her heartbeat, the blood rising toward her head, the subtle shift of pressure behind her eyes, is a quiet reminder that she's not escaping gravity, only riding it differently. If she looked down long enough, she'd see the continents move beneath her like drifting islands in an endless sea. Cities twinkle at the edges of darkness. Storms spiral like living things. The sight is not one of detachment, but connection, the awareness that she's part of the same geometry, following the same rules that pull tides, form stars, and bend light. Falling doesn't mean separation. It means belonging to the universe's most natural motion. When her capsule returns to Earth, re-entering the thickening atmosphere, the fall becomes something else again. The air pushes back, the heat builds, and at last, the ground rises to meet her. The motion that had been silent and smooth turns to roar and fire. She lands, feels the weight return, and the planet greets her not as a stranger, but as the surface she's been circling all along. The illusion of stillness returns, but she knows better now. Every moment of her life, she's still falling not downward, but inward, following the curve that holds the stars, the planets, and her own heartbeat in motion. The fall that isn't falling is the rhythm of the universe. It's the motion written into the shape of spacetime, the grace that turns gravity into poetry. Everything is falling, and everything is held, forever missing the ground. If you close your eyes and try to imagine space, what do you see? Most people picture a void blackness, emptiness, nothing at all. But space isn't nothing. It's a thing, a structure, a fabric that fills everything, even the places we think of as empty. It's not air, not energy, not matter. It's the silent geometry that allows those things to exist at all the stage on which every movement, every moment, every atom takes place. Einstein gave this stage a name, spacetime. But the word can be misleading because it sounds like two separate things, when in truth, they are one. Spacetime is not a sheet stretched under planets. It's not a film or a net or a surface you could touch. The rubber sheet image that fills textbooks is only a shadow of the idea, useful for a glimpse, but far too flat. The real thing exists in 4 dimensions, impossible to see all at once. Imagine, instead, a vast, invisible web whose threads are not strings, but directions, lines of motion, of possibility, extending through every point in the universe. When something massive enters that web, it doesn't press down as much as it changes the way the threads connect. It alters geometry itself. This is what it means to say that space is curved. It's not a dent in something physical, but a change in how distances and directions behave. In flat space, 2 parallel lines never meet. In curved space, they might converge or diverge forever, depending on how the underlying geometry twists. Mass and energy dictate that twist. A star, for instance, alters the way nearby space connects to itself, so that light traveling in what seems a straight line actually follows a loop through bent geometry. The bending is not in the light, nor in the star, it's in the stage beneath both. If you could somehow float in that space and look closely enough, you wouldn't see a fabric at all. You'd see relationships between moments, between positions, between the very concepts of here and now. The universe, at its core, is not built of things, but of the distances and durations between them. The geometry of those distances is what we call gravity. And so, when a planet orbits the sun, it's not being pulled by an invisible hand, but following the straightest possible route through a geometry that happens to be curved. Time, too, is woven into this geometry. You can't separate where something is from when it is. A moment in time is as much a coordinate as a point in space, and together they form the four-dimensional landscape of existence. When gravity acts, it bends both space and time, tilting the flow of moments just as it shapes the path of motion. This is why clocks run slower near massive objects, why time stretches near black holes, and why the universe's expansion isn't simply a spreading of matter, but a stretching of the immobility, very metric that defines what distance means. It's difficult to imagine because our senses evolved for 3 dimensions. We can picture surfaces bending, waves rippling, threads twisting, but the curvature of space-time has no perfect analogy. It's not something we see, it's something we infer. When light arcs through the sky or planets trace elliptical paths, we're watching the shadow of curvature, the way geometry reveals itself through motion. The invisible fabric shows its presence only in how things move across it. At every point in this cosmic web, there is tension, not mechanical tension, but mathematical. The distribution of mass and energy tells the fabric how to stretch and compress, how to curve inward or outward. It's a constant conversation, written in the equations of relativity. Matter shaping geometry, geometry guiding matter. Nothing exists outside that dialogue. Even empty space hums with it, because vacuum itself contains energy, and energy curves space. If you could stand inside this fabric and watch a massive star collapse, you would see the threads tightening, twisting inward, dragging the coordinates of time along with them until they spiral into a singular point. From outside, you'd see only darkness, the star's light trapped by its own geometry. From within, time would slow, stretch, and eventually lose meaning. What began as a fabric would become a funnel, deeper and steeper, until even light could not climb out. Yet, even that black hole is still part of the fabric, not a hole in it, but an extreme deformation of its shape. The most haunting truth is that you are part of this geometry too. Every movement you make, every heartbeat, every passing thought takes place inside that same interconnected field. You are not sitting on the fabric of space-time. You are woven into it. Your atoms bend it ever so slightly. The air around you, the floor beneath you, the starlight reaching your eyes, all of it is bound by the same invisible rules of curvature. The distances you travel, the seconds you live, are the geometry itself unfolding around you. The invisible fabric is not out there, beyond the stars. It is here, surrounding and containing you. It carries you the way a current carries a leaf, silent and continuous. You never feel it because you move with it, shaped by it, inseparable from it. And though we can't touch it, we touch its consequences every moment of our lives. The tick of a clock, the pull of the ground, the shimmer of light on water, all are small echoes of the same hidden structure, the one that holds the entire universe in its quiet four-dimensional weave. In the stillness of the universe, even silence has motion. Space itself can tremble, not with sound or vibration in air, but with the movement of geometry, tiny pulses that travel through the very structure of existence. These are gravitational waves, ripples in reality itself. They stretch and squeeze, Everything they touch, though so faintly that even the strongest of them alters distances by less than the width of an atom. And yet, they are everywhere, passing through you right now, through the earth, through the stars, relics of events so violent and distant that their echoes still move through the cosmos long after the sources have gone dark. When Einstein first predicted them in 1916, they seemed like a poetic impossibility, a consequence of his equations that might exist in theory, but could never be measured. He described spacetime as a fabric that could bend under the weight of matter, and like any fabric, it could also ripple when disturbed. Two massive bodies orbiting one another would send out waves, carrying energy away in the form of warped geometry. But these ripples would be unimaginably subtle, their effects buried beneath the noise of everything else. For a century, they remained invisible, an elegant idea, waiting for instruments sensitive enough to hear the faintest whisper in the roar of the universe. To understand what these waves are, imagine space-time as a vast ocean, dark and calm. When two black holes spiral together, they churn that ocean with unimaginable force, their motion twisting the surrounding geometry into waves that spread outward at the speed of light. Those waves don't move through space, they are the movement of space itself. If you could ride one, you wouldn't feel like you were traveling. You'd feel as if the universe around you were swelling and contracting in a steady rhythm. Distances would expand and shrink. Clocks would speed up and slow down, but you would not notice. Everything, including you, would be moving with the wave. The first detection came 100 years after Einstein's prediction, from an instrument so precise it could measure changes smaller than a proton's width. In 2015, at two observatories thousands of miles apart, lasers stretched down long vacuum tunnels reflected off mirrors, suspended in perfect isolation. When a gravitational wave passed through, the space between the mirrors lengthened and shortened by a fraction of a fraction of a fraction of a meter, just enough to change how the light waves interfered with each other. The signal appeared almost like a heartbeat. Two quick pulses, rising in pitch as the black holes spiraled faster and faster, then merging into one. It was the sound of two black holes colliding over 1 billion years ago, their final embrace sending ripples through the universe that finally, after all that time, reached Earth. For the scientists watching, it was a moment of awe and disbelief. Humanity had just touched a vibration born before our species existed. The instruments had recorded not just light or radiation, but the movement of space-time itself. For the first time, we weren't looking at the universe, we were listening to it. The cosmos had begun to speak in waves. Since then, more signals have arrived, some from pairs of black holes colliding, others from neutron stars, the collapsed hearts of massive suns smashing together in bursts of gravity and light. Each wave carries information about the masses, the spins, and even the distances of its creators. By tracing them, we can map the invisible, uncovering mergers too distant or dark for telescopes to see. It's a new kind of astronomy, one that senses not what the universe looks like, but how it moves. These waves are unimaginably gentle by the time they reach us. When a gravitational wave passes, it stretches the planet by less than the width of a single atom. And yet, for that instant, every mountain, every ocean, every cell in your body participates in the motion. You are stretched and compressed with the earth, in sync with the pulse of an event that may have happened before life even began here. We are not apart from the tremor. We are inside it. What's beautiful is how something so small can carry the story of something so vast. These ripples began in cataclysms that destroyed stars and reshaped galaxies, yet by the time they reach us, they are soft as breath, barely altering the geometry of our world. They remind us that violence and peace coexist in the same universe, that the quiet of the night sky is filled with echoes of unimaginable power. And if you listen closely, metaphorically or scientifically, you can sense what they mean. The universe is not static. It moves, flexes, hums with the rhythm of its own creation. Every second, waves are crossing one another, overlapping, merging into a continuous background, the faint tremble of existence. The same physics that governed the first moments after the Big Bang still plays out today, sending invisible tides across the cosmos. One day, we may detect the faintest of all the ripples left over from the birth of time itself. If we do, it will be the ultimate echo, the sound of creation frozen in geometry, still traveling outward after nearly 14 billion years. Until then, the waves we've already found remind us of something both humbling and beautiful, that the universe is alive with motion, that even the emptiness between stars is not still. The calm you feel when you look up at the night sky is an illusion. Beneath that silence, the fabric of reality is always moving. It began, as many stories of understanding do, with something ordinary, an apple, falling from a tree. Newton never wrote that it struck his head, but he did wonder why it fell straight down. Not sideways or upward, not in some random direction, but always toward the Earth's center. In that small question, he found a truth that would shape centuries of thought, that the same force pulling the apple to the ground also guided the moon in its path across the sky. The gentle fall of a fruit and the motion of a celestial body were connected by a single invisible thread, gravity. It was an idea so powerful that it bound the heavens and the earth into one continuous world. For Newton, gravity was a pull, a universal attraction between masses. Everything drew upon everything else, no matter the distance. It worked perfectly for the motions he could see, predicting tides, orbits, and planetary dances with exquisite precision. But he could never explain how that pull happened. What carried it across the void? What invisible hand reached through emptiness to connect apple and planet, moon and earth, star and galaxy? He accepted that it worked, but even he found the mechanism absurd, a mystery that nagged at the edges of reason. Centuries later, Einstein returned to that mystery and saw it not as an unseen force, but as a shape. Gravity wasn't a thread tying things together. It was the curve of the stage they moved upon. The apple's fall, he realized, wasn't caused by Earth tugging at it from below. It was simply following the geometry that Earth's mass created around it. The planet didn't pull, it bent. Space. The apple, obedient to that curvature, traced the easiest possible path through it. The same principle that guided a falling fruit also governed the orbits of planets and the fate of stars. The difference was only scale. A star, after all, is just a colossal ball of matter, and matter bends space. For most of its life, a star balances this bend with pressure, heat pushing outward from the nuclear fires within, countering the inward pull of its own gravity. But when those fires fade, when the fuel is spent, gravity's geometry wins. The star begins to collapse, not because something pulls it inward, but because the space it occupies is curving ever tighter, its own weight warping the fabric around it until there's nowhere left to go. For smaller stars, that collapse stops early, frozen into dense spheres like white dwarfs or neutron stars, matter pressed so closely together that a teaspoon would outweigh a mountain. But for the largest, the fall has no end. The curvature deepens until it becomes infinite, folding in on itself. The result is a black hole, a place where space and time are so curved that they close like a fist, trapping even light within. It is, in the most profound sense, an apple that never stops falling. To an outside observer, the collapsing star seems to freeze in time as it approaches that boundary, its light stretching, fading, slowing until it disappears. From within, time itself bends, distorted beyond recognition. The laws that govern the universe everywhere else break down, leaving only the whisper of geometry too deep to map. And yet, this monstrous end follows the same principle that guided Newton's apple, the simple consequence of matter telling space how to curve, and space telling matter how to move. The apple falls toward the ground, the star falls toward eternity. It's strange to think that the same rule spans such a vast scale, connecting the smallest act of motion to the most violent transformations in the cosmos. When you drop something, you are enacting a law that also sculpts galaxies. The apple's path, drawn by Earth's gentle curve, is a miniature echo of the curvature that once drew a star inward until it became invisible. Gravity doesn't care about size or distance or importance. It only follows the shape of reality. In this sense, every fall is a kind of story. The apple's descent is brief and quiet, ending in a thud that returns it to the soil, to decay, to life again. The star's fall is longer, grander, a collapse that can last millions of years before the final silence. But both are motions of surrender to geometry, to inevitability, to the curve of existence itself. Even the space around you right now is slightly bent by your body's mass, though you'll never feel it. You, too, are sculpting space, just as space sculpts you. Perhaps that's why the image of the falling apple has never left us. It's more than a symbol of discovery. It's a mirror of our condition. We are all falling, not in the sense of descent, but in motion through the curved tapestry of spacetime. Every orbit, every drift, every second of your life is a continuation of that fall, the same motion that binds planets to suns and stars to their destinies. The apple and the star are not different stories, but chapters of the same one. Both reveal a universe where movement and shape are inseparable, where gravity is not a force but a consequence of being. The apple's gentle arc and the star's cataclysmic collapse are expressions of the same law, the same whisper from the fabric of reality that tells everything where to go. And in that whisper lies the quiet truth that connects you, the apple, and the dying star across all scales of existence, that to fall is not to fail, but simply to follow the curve of the universe itself. When we think of nothing, we imagine absence, a blank, silent void, where no light shines and no matter moves. But in the language of physics, nothing is never truly nothing. Even in the deepest vacuum, stripped of air, dust, and starlight, space remains. It has form, it has energy, it bends, ripples, and stretches, even when nothing seems to be there. The universe, it turns out, cannot be emptied. What we call nothing still carries the geometry of everything. This was one of Einstein's strangest gifts to us. The realization that space itself is not a passive container, but an active player. Before him, most people pictured space as a kind of stage, infinite, unchanging, indifferent to the actors moving across it. Objects came and went, but the stage remained the same. Then relativity transformed that picture. Space could bend, twist, and expand. It could stretch under the weight of galaxies or contract in the pull of gravity. It was elastic, alive, responsive. The emptiness itself had texture. Imagine, if you could, removing every star and planet, every atom and photon from the universe. You might expect silence, stillness, nothing left at all. But what you would have is a vast, invisible fabric with its own hidden tension. Even devoid of matter, space would retain structure, its own curvature, its own energy. Like the surface of an ocean that can rise and fall even when the wind is gone, the vacuum of space can fluctuate, vibrating with quantum motion. What seems empty still hums faintly with possibility. At the smallest scales, this so-called emptiness is restless. Quantum fields flicker in and out of being, creating pairs of particles and antiparticles that appear, interact, and vanish in less than an instant. These virtual flashes fill all of space, forming a constant simmering background, the vacuum energy of the universe. It is so persistent that even when all else is gone, space still contains this seething potential, a kind of cosmic tension between existence and nothingness. That tension has consequences. When Einstein added a constant to his equations, the cosmological constant, he was trying to balance the universe, to keep it steady against collapse. He didn't know then that he had stumbled upon something real, a form of energy intrinsic to space itself. Decades later, astronomers would find that the expansion of the universe is not slowing down as gravity would predict, but accelerating. The culprit, it seems, is that same hidden energy, the power of empty space pushing outward, stretching the cosmos wider with each passing moment. Nothingness, in this sense, is what makes the universe grow. It's difficult to imagine space bending without something inside it to press or pull. We're used to thinking of curvature as a response, a weight on a surface, a mass tugging at geometry. But the equations don't need mass to create shape. Pure space can curve by itself. It can have positive curvature, like a sphere, negative, like a saddle, or none at all. These geometries aren't determined by what's in the universe, but by the energy and structure of the universe itself. You can see the effects of that curvature even from your small corner of existence. The universe's expansion stretches the very distance between galaxies, not because the galaxies move through space, but because space itself expands. Light from distant stars arrives, red-shifted, stretched like a thread, pulled too far because it has traveled through expanding emptiness. The shape of that nothingness dictates the journey of light, the formation of galaxies, and the fate of time. The idea that nothing can have edges is one of the quiet paradoxes of cosmology. If space curves back on itself, it could be finite yet unbounded, like the surface of a sphere where traveling straight long enough would eventually bring you home. There would be no outer wall, no barrier, just geometry looping endlessly in all directions. In that sense, even the edges of nothing are illusions, boundaries, drawn by our limited perspective. The universe may have no true edge at all, only the soft folds of space continuing beyond what light has had time to reach. And yet, even with its boundlessness, space carries memory. The shape of the cosmos today still reflects the distribution of energy it held in its first moments. The faint microwave background that fills the sky. The afterglow of the Big Bang is not just ancient light, but a map of those primordial ripples in the fabric of emptiness. What began as tiny fluctuations in nothing grew into the scaffolding of everything, the galaxies, the stars, the atoms that became us. The universe didn't arise in space. Space itself arose from the energy of that first expansion. So when we speak of the edges of nothing, we're really speaking of the structure that underlies being. Emptiness is not absence but potential, a quiet field where geometry itself becomes reality. Even in the deepest vacuum, something persists. The shape, the hum, the faint vibration of existence. It reminds us that the universe doesn't need matter to be alive. Every night, when you look up at the stars, you are not just gazing into light, but into the shape of the invisible that surrounds it. The darkness between the stars isn't nothing at all. It's a living, breathing fabric, one that flexes, expands, and remembers. And though we call it empty, it's in that emptiness that the universe hides its deepest strength. Light travels faithfully. It leaves its source and heads outward, straight as thought, carrying with it the memory of where it began. But when that light crosses the universe, it passes through a landscape that isn't flat. It drifts through valleys and over invisible hills carved into the fabric of space by gravity. The result is one of the strangest illusions the cosmos can create, a mirage not made of air or heat, but of geometry. Galaxies far behind other galaxies appear stretched, doubled, or wrapped into perfect circles of light. We call it gravitational lensing, but it is less a lens than a bending of reality itself. When Einstein first predicted it, he didn't think anyone would ever see it. He had shown that massive objects bend the space around them, and since light follows the curves of that space, its path should bend too. The effect was real but delicate, so subtle it seemed forever beyond reach. Yet in 1919, during a solar eclipse, astronomers caught the first proof. As the moon's shadow blotted out the sun, starlight passing near the sun's edge appeared displaced, shifted slightly from its true position in the sky. The sun's mass had curved the light's path, and in doing so, curved the map of the heavens. The world had just witnessed the universe's first verified illusion, a cosmic mirage painted by gravity. On galactic scales, that same effect becomes breathtaking. Imagine a distant galaxy, billions of light years away. Between it and us lies another, much closer, its mass immense enough to warp the space surrounding it like a glass of thickened reality. When the light from the distant galaxy passes through that warped region, it doesn't travel straight. It bends, wrapping around the nearer galaxy in arcs and circles. To our telescopes, the background galaxy appears duplicated, stretched into elegant curves of light called Einstein rings. The alignment has to be perfect, but when it happens, it's as if the cosmos itself is gazing through a lens of its own making. In these distortions, astronomers have found one of the most powerful tools in the universe. The light doesn't lie. It bends according to the true shape of space, not what we think is there. When the observed bending is stronger than what visible matter can explain, we know something unseen must be shaping it, something massive, yet invisible. This is how we discovered that the universe is filled with dark matter, a mysterious substance that outweighs all the stars and planets combined. It doesn't emit or absorb light, but it sculpts space nonetheless, and gravitational lensing reveals its handprint. Wherever the light arcs too sharply, wherever galaxies seem smeared across the sky, we are looking at the hidden scaffolding of the cosmos. It's an eerie beauty light that has traveled for billions of years, arriving warped and multiplied, the same galaxy appearing in several places at once. Sometimes, those multiple images arrive not even at the same moment. Because each path of light is a different length, we might see the same supernova explode in one image, and then, months or even years later, see it happen again in another. We're watching echoes across time, stitched together by the geometry of gravity. Every distorted beam carries both distance and history, whispering stories from the other side of the universe. To the eye, these arcs of light resemble threads of silk draped through space, soft and luminous. To the mind, they are maps, tracings of invisible contours in the cosmic fabric. Astronomers use them to weigh clusters of galaxies, to chart dark matter, to glimpse the distribution of mass across billions of light years. What they find is both simple and astonishing. The universe is not just filled with light and matter, but with curvature. Everywhere, space bends under the weight of what it holds, and light, honest and obedient, reveals those bends by following them. The next time you see an image from the Hubble Space Telescope, look closely at the galaxies in the background. Many of those delicate streaks and smudges are not galaxies at all, but the stretched reflections of ones hidden behind them. You're not seeing errors in the lens or distortions from glass. You're seeing the structure of reality itself. Each curve of light marks a place where gravity has shaped space so profoundly that it becomes a mirror showing us what lies beyond. And yet, there's something deeply poetic about it. Light, the fastest thing in the universe, cannot escape the shape of space. It rushes forward with perfect intent, yet it must bow to geometry. Every beam that reaches us has been touched by gravity, curved and delayed, shaped by the mass of stars, galaxies, and dark matter it encountered along the way. When we look at the night sky, we aren't seeing the universe as it is, but as gravity has painted it warped, magnified, and layered through time. These cosmic mirages remind us that seeing is not always knowing. Behind every image lies a story of motion and distortion, of light bent across unimaginable distances. What looks like a single glimmer may be a chorus of echoes, arriving from different paths, shaped by forces we cannot see. The universe, in its quiet artistry, uses light as both messenger and brushstroke. It paints its truths not on a canvas, but in the bending of the invisible, a masterpiece written in the curved language of space and time. When we speak of infinity, we imagine something without boundaries, endless, stretching forever in every direction. But even infinity can have a shape. The universe, vast beyond comprehension, isn't merely large. It has a form, a geometry written into its very being. That shape decides how galaxies move, how light travels, and even how time itself unfolds. Space may seem flat to our eyes, but its true structure is something we can only glimpse through mathematics and light stretched thin across unimaginable distances. Einstein's equations allow for three great possibilities. The universe can be closed, curved inward like the surface of a sphere. It can be open, curved outward like a saddle, or it can be flat, extending endlessly in all directions without curvature at all. Each version is infinite in its own way, yet they are not the same. A closed universe could, in theory, fold back upon itself. If you traveled in a straight line long enough, you might eventually return to your starting point, as a sailor might circle the globe. In an open universe, you would travel forever, never repeating a path through a geometry that expands eternally. And in a flat one, parallel lines would remain parallel, and the cosmos would stretch outward in perfect balance, neither collapsing nor curving, just continuing without edge or end. For most of history, the idea that the universe had any shape at all was unthinkable. It was simply there, infinite and featureless. But once Einstein showed that space could bend, cosmologists began to wonder what the overall curve of the cosmos might be. They looked to the stars for clues, not their brightness or motion, but their arrangement, the way light from distant galaxies stretched and faded as it crossed the expanding fabric of space. Every photon we receive carries information about the shape it has traveled through, and by measuring those paths, we can begin to sense the universe's geometry, the way sailors once read the curvature of the sea by the horizon's gentle fall. In a closed universe, gravity eventually wins. Expansion slows, halts, and reverses. Galaxies that once fled apart would begin drifting back together, drawn by their collective mass. Over trillions of years, the universe would contract into itself, stars dimming, time shortening, until all matter collapses into a final singularity, a big crunch. It would be a mirror of the beginning, an end that curls back into origin. Infinity, in this vision, is a loop, not endless extension, but endless return. An open universe tells a different story. Here, the density of matter is too low for gravity to stop the outward flow. Space continues to stretch, galaxies race apart faster and faster, and the night sky grows darker with time. In this version, infinity is expansion without end, an ever-widening gulf in which light grows thin and cold. The stars will burn out, leaving only remnants drifting in, a universe that never stops growing. It's a lonely kind of forever, not a circle, but a horizon that recedes faster than you can ever reach. And then, there's the flat universe, balanced perfectly between the two. Its curvature is so subtle that space neither folds back on itself nor opens outward into a saddle. Parallel lines remain parallel, triangles add up neatly, and the expansion continues forever, but just barely so. This is the geometry the evidence seems to favor, a cosmos delicately balanced, infinite in extent, but finite in what it contains. The light of the cosmic microwave background, the afterglow of the Big Bang, reveals it. When scientists mapped its faint ripples, they found a pattern that matched a flat geometry almost exactly, as though the universe were poised at the razor's edge between collapse and endless flight. It's easy to imagine these shapes as physical things, spheres, saddles, planes, but the truth is subtler. The curvature of the universe isn't something that exists outside it. There is no external space into which it bends. The curve is internal, woven into the very distances between things. When we say the universe is flat, we mean that the geometry governing those distances follows the simplest possible rules. When we say it's curved, we mean the rules themselves are bent, like lines drawn on a distorted sheet. The shape of infinity is the way the universe measures itself. And yet, even knowing this, our intuition fails us. How can something infinite be closed? How can it curve if there's nothing beyond it to curve into? These questions have no simple answer, because we are creatures of 3 dimensions trying to imagine the shape of 4. To us, infinity feels like emptiness, but to the universe, infinity is texture, a structure that allows time to move, galaxies to drift, and light to reach us from 13 billion years away. Some cosmologists wonder if the shape might change. As dark, energy drives expansion. As gravity pulls on the filaments of galaxies, perhaps the universe's geometry evolves, tilting ever so slightly toward openness. Others dream that the curve might one day fold back, creating a cycle of endless births and endings, a breathing cosmos that expands and contracts like a living thing. We don't know. What we do know is that geometry is destiny, that the future of everything depends on the bend of nothing. When you look up at the night sky, you are peering into that geometry. Every starlight shimmer, every faint smear of a galaxy is a message written in curvature. You are not gazing into a void. You are standing inside infinity's shape, part of the same fabric that stretches without end. And somewhere, far beyond what we can see, the universe continues to curve, quietly revealing that even the endless has an edge not in space, but in understanding. When we picture the universe expanding, it's easy to imagine galaxies bursting outward into empty space, like fragments from an explosion. But that image, vivid as it is wrong. The galaxies aren't flying through space at all. The space between them is what's growing. The fabric of the cosmos itself is stretching, quietly, relentlessly, carrying every cluster of stars farther from every other. The galaxies drift apart, not because they are moving, but because the distance that defines apart is swelling beneath them. It's not motion in the traditional sense. It's creation of more space, more distance, more time. At the beginning, the universe was smaller than an atom, compressed and luminous beyond comprehension. There was no center and no edge, just a boundless field expanding everywhere at once. That moment, the Big Bang wasn't an explosion that happened in space, but the sudden appearance of space itself. Every point in the universe began stretching away from every other, a cosmic unfolding that continues today. The galaxies we see scattered across the night aren't racing through emptiness. They're passengers on an ocean of expanding geometry. You can imagine it as dots drawn on the surface of an inflating balloon. As the balloon grows, the dots move away from each other, not because they're crawling along the surface, but because the surface itself is expanding. There is no central dot, no privileged point of origin. Every spot experiences the same increase in distance from all others. That's what's happening in our universe. From every galaxy's point of view, it looks as though everything else is receding, but there is no true center. The center is everywhere, and everywhere is moving away from everywhere else. For billions of years, this stretching has shaped everything. When we look at distant galaxies, their light is shifted toward red, not because they're rushing through space, but because space has expanded during the light's journey, stretching its wavelength like taffy. This redshift is a fingerprint of expansion, a cosmic record written into every photon. The farther away a galaxy is, the longer its light has traveled, and the more the space it crossed has stretched in the meantime. Some light has been stretched so much that it has slipped out of the visible spectrum entirely, becoming a whisper of microwaves, the faint afterglow of the universe's first fire, still reaching us today. For a long time, Astronomers thought this expansion might slow with time. Gravity, they reasoned, should tug at the galaxies, pulling them together, perhaps even halting the cosmic stretch someday. But when scientists measured the expansion in the late 20th century, they found something startling. The stretching is speeding up. Space isn't just growing, it's accelerating, as though something unseen is pushing it apart. That mysterious force is what we call dark energy, a pressure woven into the vacuum itself, so subtle we can't touch or see it, yet strong enough to decide the fate of the universe. If this acceleration continues, the cosmos will grow colder and lonelier. Galaxies already far away will slip beyond our reach, their light redshifted until it disappears into darkness. Future observers, billions of years from now, might see only their own galaxy, unaware that countless others ever existed. The expansion doesn't tear apart galaxies or solar systems. Gravity keeps those small islands intact, but the vast oceans between them widen endlessly, and every shore grows farther from every other. The night sky, we know, is temporary, a moment in cosmic history when the universe was young enough for its light to still find us. Even now, as you sit here, the space between your eyes and the distant stars is stretching, not by much on human scales. The effect is imperceptible, but over cosmic distances, it defines everything. The Andromeda Galaxy, our nearest major neighbor, is close enough that gravity overcomes the expansion. It's actually moving toward us. But beyond our local cluster, the stretching dominates. Every galaxy we can see is receding, the fabric between us and them expanding faster than their light can close the gap. It's a humbling idea that space itself can grow. It means the universe isn't expanding into anything. There is no outside, no boundary it's pushing against. The expansion is intrinsic, a swelling of the metric that measures distance itself. If you could freeze time and draw a grid through space, the lines would lengthen as the universe expands, carrying everything with them. There's no wind of motion, no sense of travel, only the quiet, steady widening of reality's weave. The stretching of space is also the stretching of time. As the universe expands, its clock slows on a cosmic scale, cooling and calming as energy spreads thinner. What began as a blinding, turbulent fire has become a vast, dark ocean, where galaxies are the last glowing embers, drifting apart. Yet even as it thins, the universe remains whole. Every expansion, every widening gap is balanced by the same unbreakable thread of connection, the geometry of space-time itself, stretching yet never tearing. When you gaze at the night sky, you're not looking across empty distance. You're seeing space in motion, a living fabric that's been expanding for nearly 14 billion years. The starlight that reaches you has traveled through that growing sea. Its color changed, its energy softened by the expansion of everything. Each glimmer is a message from a past when the universe was smaller, denser, younger. You are not apart from that expansion. You are part of it. Every breath, every heartbeat, every second of your life unfolds within a universe that is still, at this very moment, stretching. And though the stars seem still, they are being carried away by the quietest force imaginable, the widening of space itself, the infinite exhale of the cosmos. There is a rhythm to the universe so slow that no living creature could ever hear it. It is the long, drawn-out inhale and exhale of existence itself, the steady breathing of space and time. For billions of years, the cosmos has been expanding, the distances between galaxies growing larger, the fabric of reality stretching thinner. But in the last few decades, we discovered something astonishing. The universe isn't just expanding, it's accelerating. The rate of that cosmic breath is increasing, as if some unseen force were quietly pressing outward from every corner of creation. We call that force dark energy, though the name carries more mystery than meaning. It is not a substance, not a gas or a wave, not even a form of matter as we understand it. It is more like an intrinsic property of the universe, a pressure woven into the vacuum, a whisper from the fabric of space itself. Wherever there is emptiness, dark energy resides, and the more space grows, the more of it there is. It is as though the act of expansion feeds the very thing that drives it, a self-sustaining loop written into the geometry of the cosmos. When Einstein first introduced his equations of relativity, he included something called the cosmological constant, a term that would keep the universe static, preventing it from collapsing under its own gravity. Later, when astronomers discovered that the universe was expanding, he dismissed the idea, calling it his greatest blunder. Yet decades after his death, the constant returned, not as a mistake, but as a revelation. The expansion was real, and not only real, it was speeding up. What Einstein had tried to suppress was, in fact, the very breath of the universe. The discovery came quietly in the late 1990 seconds, when two teams of astronomers studying distant supernovae noticed that the light from those ancient explosions was dimmer than expected. The galaxies hosting them were receding faster than gravity alone could explain. The universe, rather than slowing down as it aged, was pulling itself apart with increasing speed. That acceleration defied every intuition, every known law of motion. It was as if some invisible hand were pushing outward, stretching the cosmic fabric faster and faster with time. Dark energy is the name we gave to that push, but the truth is, we don't know what it is. It could be the cosmological constant. Einstein imagined a fixed energy density of empty space, or it could be something dynamic, an evolving field that changes as the universe grows. Some physicists see it as the pressure of the vacuum itself, an echo of quantum fluctuations bubbling just beneath reality's surface. In that view, even the void isn't truly empty. It seethes with virtual particles appearing and vanishing, each tiny fluctuation adding its weight to the expansion. Others suggest dark energy might be a property of gravity itself, a sign that our understanding of space-time is incomplete. Whatever it is, dark energy now dominates everything. About 70% of the universe's total content is this invisible pressure, with dark matter making up most of the rest. Ordinary matter, the atoms that form stars, planets, and people, accounts for less than 5%. We live in a universe ruled not by what we can see, but by what we cannot. Every second, it expands a little more, galaxies slipping quietly away beyond the horizon of light, vanishing into a distance that grows faster than their photons can cross it. To future observers, billions of years from now, the sky may appear almost empty, their galaxy floating alone in darkness, unaware that others ever existed. The idea that space itself has pressure that the vacuum can push sounds paradoxical, but gravity and pressure are two sides of the same curvature. In general relativity, energy bends space, and space tells energy how to move. The vacuum, filled with this latent energy, exerts a kind of negative pressure, stretching rather than pulling. The more it stretches, the weaker gravity's grip becomes. It's as if the universe is caught in a quiet contest between attraction and expansion, and the latter is slowly winning. In a strange way, dark energy defines the fate of time itself. If expansion continues to accelerate, galaxies will drift beyond one another's reach, stars will fade, and the universe will cool toward silence. Time, which depends on change and motion, will lose meaning in a cosmos where nothing interacts. This future, sometimes called the heat death, is not fiery or explosive, but tranquil. A universe breathing outward until its last exhale, its pulse slowing, its rhythm fading into stillness. Yet there's something oddly peaceful in that vision. The same forces that allow galaxies to form and light to shine are the ones that will eventually carry them apart. The expansion that began with a sudden surge of creation may end not with collapse, but with diffusion, the quiet settling of everything back into equilibrium. It's the long breath of the universe reaching its final, infinite sigh. Even now, you are part of that breath. Every atom in your body drifts with it. The space between your molecules, between your planet and the stars, between the galaxies themselves, is stretching as you read this. It's not something you can feel, but it's there. A silent tide that has been rising for billions of years. And when you look up at the night sky, what you're seeing is that expansion frozen in light, the record of the universe's inhale, caught mid-motion. The cosmos is still breathing, softly, endlessly, and in that breath lies the quiet heartbeat of everything that has ever been. At the heart of every galaxy, hidden behind veils of dust and silence, there is a place where space stops behaving. It is not a thing in the way we think of things, not an object, not a surface, not even a place that can truly be entered. It is a region where the curvature of space folds so completely inward that the rules that govern direction, time, and distance simply dissolve. This is a black hole, a wound in reality, carved by gravity's endless hunger. When a massive star exhausts its fuel, its light fades, and its core collapses, nothing can resist the implosion. The matter falls inward, the atoms crushed, the protons broken, until there is no structure left to hold it apart. All of its mass, all of its energy, is squeezed into a point of infinite density, and the space around it curves steeply toward that center. At a certain distance, the curvature becomes so extreme that even light cannot escape. That boundary is the event horizon, not a surface of matter, but a limit in geometry, a place where every path forward leads deeper in and none return. To an outside observer, the approach to the horizon happens in slow motion. A falling object appears to freeze, its light growing, dimmer and redder as it struggles against the pull of gravity. Time itself stretches. Seconds near the black hole pass like centuries to those far away. To the object, though, the fall continues normally. There is no sense of crossing a border, only the smooth continuation of descent. It's space that betrays it, folding inward so sharply that all possible futures point to the center. In that directionless interior, the concept of where stops being meaningful. Einstein's equations predict that the curvature continues until it collapses into a singularity, a point where the density becomes infinite and the known laws of physics fail. Here, spacetime folds so tightly that it can no longer describe itself. We can't see inside, not because it's dark, but because the idea of inside doesn't quite exist. Every direction leads toward the singularity. There is no escape, no opposite, no distance that can be measured. Time, too, becomes strange. The future and the center are the same destination. For anything that crosses the horizon, falling isn't something that happens in time. Falling is time. And yet, for all its destruction, a black hole is not empty. Around its edge, matter forms luminous disks as it spirals inward, heating to millions of degrees, releasing light and radiation across the universe. These accretion disks are among the brightest things in existence, brilliant halos encircling perfect darkness. It's an exquisite irony. The most radiant regions of the cosmos form around the deepest voids. From far away, the warping of space bends that light into rings, echoing back the structure of the invisible. The event horizon, sharp and clean in mathematics, becomes a soft silhouette in reality, its edge a trembling mirage of distorted starlight. When two black holes meet, they merge in a slow, spiraling embrace that sends ripples through space-time itself. For eons, they orbit one another, drawing closer as they lose energy. Through gravitational waves, faint tremors in the fabric of existence that spread outward at the speed of light. When they finally collide, the event horizons fuse, and space quakes in a single powerful pulse that can travel across the universe. We can detect those ripples now, faint oscillations in reality that let us hear the dance of invisible giants. It's as if the universe itself hums with their final movement. Despite their reputation as destroyers, black holes also give order to the cosmos. They anchor galaxies, holding stars in orbit with their immense gravity. Without them, the spiral arms of the Milky Way would drift apart. The dance of creation and collapse would lose its rhythm. Even our own galaxy has a black hole at its center, silent and steady, its presence defining the motion of everything that surrounds it. We orbit within its influence, tracing the edge of its unseen pull. For all we've learned, there remains a veil we cannot lift. The singularity hides, not just matter, but information itself. The universe has a law that information cannot be destroyed, yet black holes seem to defy it. Physicists call this the information paradox, a mystery that sits at the intersection of gravity, quantum theory, and time. Some believe the data of what falls in remains encoded in the surface of the event horizon, stretched thin across its edge, like writing on a cosmic membrane. Others suspect that space and time themselves are incomplete, that black holes point toward a deeper layer of reality yet undiscovered. To imagine a black hole is to imagine the limits of what can be known. It is not a hole in space, but a region where space itself collapses inward, where time loses sequence, where gravity becomes geometry's own undoing. It is the final proof of how far curvature can go, from gentle bends that hold planets in orbit to the ultimate fold that erases meaning. And yet, within that darkness, the universe continues to move with grace. Matter falls, light bends, waves echo. The dance of black holes is not the end of structure, but its renewal, gravity's way of sculpting the infinite into something both terrible and beautiful. They are reminders that space can turn upon itself, that even in the deepest shadow there is motion, and that the same laws that let an apple fall to the ground can also fold an entire star into silence. Time is not the steady river we once imagined. It moves, yes, but not at the same pace everywhere. It bends and stretches like space itself, flowing faster or slower depending on where you stand in the universe's invisible geometry. On Earth, it feels constant, a heartbeat, a sunrise, a ticking second hand. But that constancy is an illusion. Even here, under the blue dome of our sky, time runs differently from one place to another. The curvature of space around our planet is subtle, but it is enough to make every clock, every pulse, every signal dance to a slightly different rhythm. Einstein revealed this quiet truth over a century ago. Gravity, he said, is not a force pulling downward, but a warping of space-time itself. Mass bends the fabric of the universe, and that bending affects how quickly time passes. Where gravity is stronger, closer to a massive body, time slows down. Farther away, where space is less curved, it speeds up. This isn't a metaphor or a trick of perception. It's measurable, real, and essential to the functioning of the modern world. Without accounting for it, even your phone would lose its sense of place within minutes. Orbiting high above you are satellites that circle the Earth, quietly keeping time. They're part of the global positioning system, the network that allows your phone to tell you exactly where you are. Each satellite carries atomic clocks that measure time with incredible precision, ticking billions of times per second. But because they're farther from Earth's center, where gravity is weaker, those clocks run slightly faster than the ones on the ground. Not by much, just about 45 microseconds per day, but enough that, without correction, the system would fail. Within a single day, your GPS location would drift by miles, your navigation lost to the tiny, relentless curve of space-time. To fix this, the designers of GPS built Einstein's relativity directly into the system. They slowed the onboard clocks before launch, calibrating them to run at a pace that would appear synchronized once they reached orbit. Every signal, every timestamp your phone receives is adjusted for both special and general relativity, the twin effects of motion and gravity on time. The network is a symphony of clocks, each ticking at its own rate, yet perfectly tuned to create the illusion of a single, universal rhythm. The technology that guides you down a street or across an ocean works only because we've learned that time itself bends with the weight of the world. Even here, on Earth, that difference exists. A clock at the top of a mountain runs faster than one at sea level. The higher you go, the farther you are from the planet's center of mass, and the weaker gravity's pull becomes. The difference is minute nanoseconds in a day, but precise enough that scientists have measured it using atomic clocks. It means that your head is aging slightly faster than your feet, that astronauts aboard the International Space Station, orbiting just beyond the densest curvature, experience time at a subtly different rate than you do right now. They return to Earth younger by fractions of a second, proof that even a small change in gravity can stretch the fabric of time itself. You don't notice it, of course. Your heartbeat doesn't slow or quicken as you climb a hill. Your thoughts don't drift differently in the mountains than at the shore. But if you could somehow see the world's clocks all ticking together, one on a satellite, one in valley, one beating inside your chest, you would see them diverge ever so slightly, their ticks drifting apart in ways only the equations of relativity can predict. Time is not a single thread running through the universe. It's a vast web of local strands, each tied to the curvature of its own surroundings. That means your life, too, unfolds along a unique timeline, shaped by the gravity that cradles you. You are moving through a field that subtly bends your seconds, just as it bends light and motion. The deeper you sit within Earth's gravity well, the slower your clock ticks compared to someone high above the clouds. The difference is too small to feel, but it's there in every oscillation of your atoms, every flicker of thought, every pulse of blood. Time dilation is not confined to black holes or cosmic extremes. It happens here, around you, always. And though the scale is tiny, the implication is profound. It means time is personal, stitched into the geometry of where you are and how you move. No two observers share exactly the same moment. Each experiences a slightly different tempo of existence. The universe, in this way, is like a great concert of clocks, none perfectly in sync, yet all part of the same expanding melody. We tend to think of technology as our creation, our triumph over nature, but the devices that navigate our world, the satellites, the circuits, the signals only work because they obey the natural laws we once doubted. Every time your phone guides you home, it's whispering a truth Einstein uncovered, that even in the calm, familiar gravity of Earth, time is bending under your feet. It's humbling to realize that the simple act of knowing where you are depends on understanding that time is not the same everywhere. The universe does not beat to a single clock. It sways, it drifts, it stretches with the curvature of space. From your pulse to the orbit of satellites, from mountain peaks to ocean depths, everything that lives and moves does so within a fabric that never stands still. The seconds you feel, steady and sure, are part of a cosmic choreography, the slow dance of time itself, bending gently beneath your every step. For most of human history, we assumed the universe was flat. Not flat like a sheet of paper floating in nothingness, but flat in its logic. The kind of flatness that made sense when you drew a triangle, when you looked out at the horizon, when you trusted that parallel lines never meet. Euclid's geometry, carved into our minds since antiquity, told us that the rules of space were simple and eternal. The shortest distance between 2 points was a straight line. The angles of a triangle always added up to 180 degrees. But when the universe revealed its true shape, those rules began to bend. Space, it turned out, was not what our eyes or our instincts had been built to see. Einstein was the first to give that intuition form. His theory of general relativity transformed geometry from an abstract language into the living architecture of reality. Space wasn't the stage. It was part of the play. Mass and energy didn't merely move through it. They shaped it, stretching and warping it like fabric. What seemed like straight lines could curve invisibly through that fabric, their paths bent by gravity's presence. Even light, which we once thought immune to influence, obeyed the same geometry. The universe had been hiding its curvature in plain sight all along, but understanding that space could be curved was only the beginning. The harder question was, how curved is it? Is the universe bent inward like the surface of a sphere? Does it saddle outward, open, and infinite? Or does it balance, perfectly flat, on the largest scales? The answer would tell us something profound, whether the cosmos would one day collapse under its own weight or expand forever into cold emptiness. To measure curvature, scientists turn to the oldest light in existence, the cosmic microwave background, or CMB. It is the faint afterglow of the Big Bang, a whisper of radiation left over from when the universe was just 380,000 years old. It fills every inch of the sky, invisible to the eye but detectable by instruments sensitive enough to hear its static. Embedded in that radiation are tiny fluctuations, slight variations in temperature that trace the seeds of all future galaxies. If the universe were curved, those patterns would appear distorted. The geometry of space would stretch or compress them in ways we could measure. So astronomers built satellites to map that ancient light. COBE came first, then WMAP, and later the Planck Observatory, each one sharpening the picture. What they found was astonishing. The universe, on the grandest scales we can observe, appears almost perfectly flat. The ripples in the CMB fit the predictions of a geometry where parallel lines stay parallel, where triangles behave as if drawn on an endless plane. But the word almost carries the weight of everything we don't yet understand. Even the slightest curvature too small to detect could change the fate of the cosmos billions of years from now. To grasp what curved space means, it helps to step away from our two-dimensional imagination. Picture standing on Earth and drawing a triangle from the North Pole to the equator, then east along the equator, and finally back to the pole. The angles of that triangle add up to more than 180 degrees. The surface isn't flat, and the geometry reveals it. Now imagine trying to draw that triangle, not on a globe, but through the vastness of the universe, using beams of light instead of lines. The same principle applies. By measuring how light travels and how far it diverges, we can tell whether space itself curves back on itself, spreads apart, or stays in balance. Euclidean thinking fails us here, because it was born in a world too small to reveal the truth. On a table, or a field, or even a planet, space feels flat. The deviations are too gentle to see, but stretch your view to billions of light years, and the assumptions crumble. Parallel lines may converge. Straight lines may not stay straight. Even up and down lose their meaning when the curvature is part of the fabric itself. The universe is not a flat sheet spread across a void. It is a vast, self-curving structure whose edges may not exist at all. That's why you can't draw a true map of the cosmos on a flat surface. Every projection distorts something, shape, distance, or scale, because space itself resists being flattened. The same way no globe can be perfectly laid out on a map without stretching the continents, the universe can't be represented without compromise. The curvature is baked into its being, and any attempt to unfold it misses the essence of what it is, a geometry without an outside. And yet, for all the complexity, there is something deeply poetic in the balance we find. The universe hovers near perfect flatness, as if fine-tuned between collapse and eternal expansion. Inflation theory, the idea that the universe expanded faster than light in its first moments, may explain that perfection, ironing out any initial wrinkles in its fabric. But still, the near flatness feels uncanny, as though reality itself is poised on a razor's edge, neither bowed nor broken. When you look up at the night sky, the stars seem scattered across a vast black canvas. But what you're really seeing is light tracing paths through curved space, stretched over billions of years by the geometry of existence. Every photon that reaches your eyes has traveled not in straight lines, but through a gentle warp, shaped by the unseen contours of mass and energy. You're not looking at a flat picture. You're standing inside a map that can never be drawn flat. The cosmos isn't something you can chart from the outside. It's something you move through a living geometry that carries you, bends you, and includes you in its shape. Every time you look at the world, you are seeing through bent light. It bends as it passes through air, through glass, through the layers of the atmosphere that cradle the planet. It bends when it brushes the curve of the Earth's gravity, just enough to shift the edges of the horizon, to stretch the glow of a sunset beyond where the sun truly is. The light that reaches your eyes is never quite straight. It has traveled through invisible distortions, woven through curvature, both gentle and immense. Your vision, every color, every shimmer, every flicker of dawn is shaped by gravity itself. We tend to think of gravity as something that pulls on objects, a downward tug that keeps our feet on the ground. But what it really does is curve the space around us. And light, ever obedient to the geometry of the universe, follows those curves. Even the Earth, modest in its mass compared to the giants of the cosmos, bends light enough to make the world appear subtly different from what it is. When the sun sets, it is already below the horizon. The orange disk you see slipping away is a mirage born of refraction and curvature. Sunlight bent through the thickening layers of atmosphere and the soft warp of spacetime around our planet. You are watching a ghost of the sun, a memory delayed by light's passage through bent reality. The bending of light is what allows the sky to blush before the dawn. As sunlight enters the atmosphere at a shallow angle, it slows, scattering into the reds and purples that paint the horizon. The air itself acts like a lens, bending light toward you even after the sun is gone. Without that curve, twilight would end sharply, a clean line between day and night. Instead, we are given a gradual fade, the soft, aching transition of one world into another. Even here, curvature gives us beauty. Every star you see has been shaped by this same rule. Their light leaves them in straight lines, but on its way to you, it bends ever so slightly in the gravitational field of the Earth, the sun, and every massive object in between. The starlight that reaches your eyes carries the record of those bends, each one a small whisper of the universe's structure. When the light of a distant star grazes the sun during an eclipse, it arcs just enough for astronomers to measure it, the same experiment that confirmed Einstein's theory in 1919. The starlight appeared shifted, displaced from where the star truly was, proving that even light, the fastest thing in the universe, cannot escape the shape of space. It's strange to think that your very act of seeing depends on this bending. Without curvature, light would pass through the atmosphere unaltered, the sun would rise and set abruptly, and rainbows would never form. The spectrum of colors that arches after a storm exists because light bends differently for wind. Different wavelengths, red separating from blue, order unfolding from a simple curve. The same rule that bends starlight also paints rainbows across our skies. On a grander scale, this bending becomes the artist of the cosmos. Massive galaxies bend the light of those behind them into arcs and rings, cosmic mirages that stretch across millions of light years. But here on Earth, the same law shapes the delicate details of our days. When you watch a mirage shimmer above hot asphalt, you're seeing light refracted through layers of air at different temperatures, bending toward cooler, denser layers. The distant puddle that isn't there, the desert lake that vanishes as you approach, all are tricks of bent light. The world you perceive is never entirely what it seems. Even the stars twinkle because of curvature. As their light passes through turbulent pockets of air, it bends chaotically, the image shifting and dancing before it reaches your eyes. The atmosphere blurs and distorts the heavens, turning perfect points of light into living, trembling things. Astronomers build observatories high on mountaintops or in orbit, not to get closer to the stars, but to escape the bending that our air imposes. To see clearly, they must rise above the lens of the world. And yet, there's something intimate in this distortion. Every sunset, every flicker of starlight, is a reminder that we live within the geometry of the universe, not apart from it. We are inside the curvature, seeing through it, shaped by it. The air above us, the gravity beneath us, the light that dances between them all are parts of the same continuous fabric. When you lift your gaze to the night sky, you are not looking through empty space. You are peering through a gently curved window, one molded by Earth's mass, by the thickness of its air, by the invisible structure that binds everything together. If you could somehow remove the bending, the world would look alien. The horizon would shrink. The stars would stand still. The warmth of twilight would vanish. The softness of the sky, the slow burn of sunrise, the lingering light of evening, all would disappear into a sterile geometry. The universe would become a place of perfect lines and edges, but it would lose its depth, its shimmer, its illusion of infinity. The bending of light is not an imperfection. It's the reason we see beauty at all. Every gleam on water, every halo around the moon, every glint in a tear owes its existence to curvature. Gravity shapes not only the paths of planets and galaxies, but the moments of wonder that flicker through your eyes each day. The light that enters you has been bent by air and space and time, touched by the weight of the world before it ever reaches your gaze. And when you look back at the stars, that same light, reflected from your own eyes, bends once more another small ripple in the endless geometry of seeing. There's a moment, quiet and rare, when the enormity of the universe feels close enough to touch, when the knowledge of how space bends and time stretches begins to fold inward, turning from physics into feeling. To understand curvature is to see that nothing stands apart. Every atom, every heartbeat, every glimmer of thought sits within the same geometry that guides the stars. The universe doesn't just surround us, it includes us, shaping us with the same invisible hand that shapes galaxies. The more deeply you grasp that truth, the harder it becomes to see yourself as separate from anything at all. Einstein's equations describe how mass and energy bend spacetime, how the presence of something changes the shape of everything else around it. It's easy to think of that as an abstract rule, a mathematical dance between planets and light. But when you look closer, you begin to sense something more intimate. Every motion, every word, every act of kindness or cruelty leaves its own small impression on the fabric we share. The geometry of the universe is not cold or distant. It's participatory. You bend the world around you, and it bends you in return. If you've ever felt the gravity of a moment the way time seems to slow in joy or grief, the way distance between people can feel like a physical stretch, you've felt echoes of that truth. Space and time are not fixed, neither are we. Emotion changes perception just as mass changes curvature. A second can feel eternal. A lifetime can pass in an instant. The same relativity that governs the stars pulses quietly through every human experience. Our hearts are small mirrors of the cosmos, beating in rhythm with its endless expansion and contraction. There's comfort in realizing that even the vastness above follows the same patterns that unfold within us. The curvature that holds planets in orbit also holds people together. Love, grief, awe. They are forms of gravity in their own right, invisible fields that draw lives into orbits of shared experience. We move around one another, sometimes colliding, sometimes drifting apart, our trajectories altered by the unseen forces of connection. To live is to feel that pull, to surrender to it without fully understanding it. When you step outside on a clear night and look up, the stars appear scattered in stillness, but their light has been bent across space and time, their paths shaped by the masses they passed, the gravity wells they skirted, the expanding fabric that carried them. The photons that strike your eyes have followed curves you can't trace, journeys that began before the Earth existed. You, standing there in the dark, are part of that same geometry, not an observer outside it, but but a point upon its surface, as subject to its bending as the light itself. The beauty of this realization lies in how it dissolves the illusion of separation. We spend our lives dividing the world into out there and in here, the cosmic and the personal, but the line between them doesn't exist. The same curvature that governs galaxies governs you. The same physics that lets space ripple with gravitational waves lets your body ripple with breath. When you inhale, you draw in the remnants of stars. When you exhale, you return them to the air. Every thought you have is made possible by fields and particles that once belonged to distant suns. The geometry of the universe is written through you, not around you. And yet, for all its vastness, the universe is not indifferent. It allows for tenderness, for awareness, for the miracle of understanding itself. Somewhere in its curvature, consciousness arose, the ability for matter to look back and see the pattern it belongs to. You are the universe, recognizing its own geometry, a small patch of curved space-time capable of wonder. When you gaze at the Milky Way, it is not you looking at it, but it looking at itself through your eyes. Understanding curvature changes more than how you see the stars. It changes how you see meaning. Straight lines and certainty give way to arcs and flow. Life is not a flat journey from one point to another, but a path through a bending landscape, one shaped by both gravity and grace. We are all travelers on that curve, carried along by invisible forces, connected in ways too deep for language. To love, to lose, to dream, these are not deviations from the universe's order. They are expressions of it. The equations that describe curvature are simple, elegant, and impersonal. Yet they reveal a cosmos that allows for softness. The same laws that govern black holes and galaxies also allow a sunrise to blush over an ocean or a tear to catch the light. The geometry that shapes reality also shapes the quiet moments in which we feel most alive. Perhaps then, the greatest gift of understanding how space bends is the humility it brings. We are small, yes, but not insignificant. We are part of the same structure that cradles the stars. Every action ripples outward. Every feeling alters the shape of our shared space, however slightly. The universe is not something we exist within. It is something we participate in a vast, curved symphony of being, and we are both its listeners and its notes. And if you ever feel lost, adrift in the enormity of it all, remember this. Space curves around everything that has mass, and emotion curves around everything that has meaning. The universe is not straight, nor are we meant to be. We are meant to bend toward one another, toward understanding, toward the quiet, impossible beauty of being part of the same unfolding shape. The universe is not silent. Beneath the hum of stars and the whisper of cosmic radiation, the space itself vibrates with a music we can't hear directly, but can feel in the mathematics of its motion. These are the sounds of gravitational waves, ripples in the fabric of reality, traveling outward from cataclysms too vast for language. When two black holes collide, or neutron stars spiral together in their final, fiery moments, space-time shudders. The tremors spread through the cosmos like waves across a dark sea, stretching and compressing everything in their path. They pass through you, through the earth, through every atom, though so faintly you'll never notice. Yet when we capture them and translate their rhythm into sound, the universe reveals its heartbeat. Imagine space not as emptiness, but as a vast, invisible ocean. Every star and planet floats upon its surface, their masses stirring the geometry beneath them. When massive bodies move, they send ripples across that ocean. Those ripples carry information not as light does, but as motion, the pure deformation of reality itself. They do not travel through space. They are the movement of space. And unlike sound in air, which fades with distance, gravitational waves can cross billions of light years without losing their form. Each wave is a message from an ancient event, a vibration of space-time preserved like music trapped in crystal. For most of human history, these waves were only theory. Einstein predicted them in 1916, hidden in the mathematics of relativity. But he doubted they would ever be detected. They were too small, too fleeting. A passing gravitational wave changes the length of a 4-kilometer tunnel by less than 1,000th the width of a proton. It seemed impossible to measure such a whisper, and yet, a century later, we did. In September 2015, 2 observatories, one in Louisiana, one in Washington, felt space tremble. Their lasers, suspended in vacuum arms miles long, detected a faint oscillation in the interference of light. It lasted just a fraction of a second, a subtle rise in pitch that scientists converted into sound. What they heard was a chirp, simple and brief, the death cry of 2 black holes merging 1 billion years ago. For the first time, humanity didn't just see the universe. We heard it. That sound, faint and otherworldly, was more than data. It was the direct translation of geometry into music. Space itself had moved, and we had listened. Since then, we've recorded many more, each one distinct, each a note in the cosmic symphony. Some are deep and slow, like the tolling of invisible bells. Others climb quickly in frequency, spiraling upward as the black holes whirl faster and faster before their final collision. If you could compress the history of these signals into a single song, it would be both haunting and beautiful, the music of gravity's dance. What makes these waves so profound is that they carry more than sound. They carry truth untouched by light. Light can be absorbed, scattered, delayed, but gravitational waves travel through everything unimpeded. They bring us stories from places no telescope can see, from regions shrouded by the very gravity that created them. Through these vibrations, we can sense the unseen black holes merging in the dark, neutron stars, colliding in blinding bursts of gamma rays, the echoes of ancient cosmic storms that shook the universe before the first galaxies formed. When scientists play these signals for the human ear, the result feels eerie in its simplicity. A quick whoop, rising, falling, gone. It lasts less than a heartbeat, but within that heartbeat lies the energy of suns multiplied beyond measure. The collision that produced that sound released more power than all the stars in the universe combined. For the briefest instant, it is humbling to think that such violence produces something so quiet, and yet there's something tender about it too. The fact that the universe, in all its vastness, we can sing in frequencies. We can translate and hear that the tremor of 2 dying stars can cross 1 billion years and arrive as a sound you could play. On a piano feels like a reminder that we are not separate from it. The waves that pass through us now are the same ones that rippled through the distant past, shaping galaxies, altering orbits, whispering of creation and collapse. Listening to the universe this way changes how you imagine it. It's no longer a silent expanse of stars, but a living medium, alive with motion. Each wave is part of a larger rhythm, the slow breathing of existence, the expansion and contraction of space, the eternal pulse of change. We are immersed in that rhythm, part of its resonance, vibrating ever so slightly as the cosmos moves. One day, we may detect the faintest waves of all the murmurs from the universe's first moments. When space itself was born, those primordial vibrations would be the earliest sound, the echo of the Big Bang's inflation, frozen into the fabric of time. To hear them would be to listen to creation itself, to the instant when geometry began its first motion. Until then, we listen to what we can. Each new detection is another note, another line in the universe's song. And somewhere between the frequencies, between the rise and fall of space's invisible melody, you can almost sense what it means to exist here. A brief vibration within a vast and ongoing music, one that began long before us and will continue long after, echoing forever through the shifting fabric of the cosmos. Long before there were stars, before light itself had a place to shine. The universe was a smooth and silent expanse. A vast sea of energy and potential stretched thin across all directions. There were no galaxies, no atoms, no boundaries between anything, yet even in that near-perfect uniformity, there were ripples. Tiny irregularities, slight bends in the young universe's fabric, would become the scaffolding for everything that would one day exist. Those bends were small, infinitesimal distortions of spacetime. But over billions of years, they became the blueprint for stars, planets, oceans, and eventually, the living matter that would open its eyes and wonder where it came from. When the Big Bang released its first breath, it wasn't an explosion in space. It was the expansion of space itself. The cosmos inflated outward, faster than light could travel, stretching quantum fluctuations into macroscopic wrinkles. Some regions ended up ever so slightly denser, a little more curved, a touch heavier in their gravitational pull. Those tiny imperfections, magnified by time and gravity, drew matter inward. They broke the symmetry of the early universe. Without them, everything would have stayed evenly spread, too smooth for stars or galaxies to form. It's strange to think that imperfection, that slight bending of the uniform, is the reason there is something instead of nothing. As space cooled and expanded, gravity began to weave its slow design. In regions where curvature was strongest, hydrogen gathered first, drawn together by its own mass. The atoms fell toward one another, compressing, heating, spinning. In those invisible nests of curvature, the first stars were born. Their light ignited the darkness, marking the universe's transition from uniform glow to structured brilliance. The geometry of the cosmos had sculpted pockets of creation, each star a bright knot in the curve of space-time. But the bending didn't stop there. Stars lived and died, collapsing under their own gravity, exploding in supernovae that scattered heavy elements into the void. Each cycle of destruction and rebirth was guided by curvature, the inward pull of gravity shaping clouds of gas, the expanding shock waves bending space in their wake. Over time, the architecture of existence became more intricate. Galaxies formed along filaments of dark matter, vast cosmic threads where gravity's curvature was strongest. The universe began to resemble a web of luminous knots of stars connected by invisible bridges of mass, stretched across hundreds of millions of light years. Every atom in your body can trace its ancestry to those curvatures. The carbon in your cells, the oxygen in your lungs, the calcium in your bones, all were forged in the heart of stars, born from the bending of space. Each element was carried across the cosmos by explosions that rippled through the geometry of reality. Even now, those ripples continue to travel, the echoes of ancient collapses passing silently through you. The space around your atoms is not flat. It is shaped by the same cosmic tension that sculpted the first galaxies. You are made of curvature, condensed and cooled into form. The more we understand about the early universe, the more it seems that curvature is not just a background feature of reality, but its essential design principle. Space bends under the weight of matter, but matter also arises from those bends. Energy condenses where geometry twists. Particles emerge where tension folds the vacuum. Existence itself seems to be the result of space learning how to curve. It's not so different from how a piece of paper, when bent, becomes three-dimensional, how a simple surface finds structure when it folds. The universe found its complexity through that same gesture, each curve adding depth, each distortion giving rise to something new. Even the Milky Way, our cosmic home, is a product of this delicate dance. It spun itself into a spiral over billions of years, drawn together by invisible threads of gravity that looped through space. Every turn of its arms, every cluster of stars, every drifting nebula follows the shape of curvature laid down in the beginning. And here, within one of those spiraling arms, our sun formed. Around it, the remnants of previous stars gathered into planets. On one of those planets, chemistry became biology, and biology began to look up. You, reading these words, are the latest expression of that curvature, a ripple grown conscious of its own shape. The neurons firing in your brain follow paths sculpted by the same physics that guided galaxies into form. When you think, when you breathe, when you fall in love, you are participating in the same architecture that governs black holes and starlight. The bending that made the cosmos also made you capable of perceiving it, and it continues still. Space is expanding, stretching its curvature outward. The galaxies drift farther apart, carried by the momentum of that original unfolding. But the memory of the first bends remains written in everything that exists. Every mountain, every ocean, every particle of dust carries the record of the universe learning to shape itself. The architecture of existence is not finished. It's ongoing, an endless act of becoming. Perhaps the most extraordinary thing is that the universe never stopped bending toward complexity, never stopped finding ways to fold energy into meaning. From ripples in the void came stars, from stars came atoms, from atoms came life, and from life came awareness, the ability to look back and see the curve itself. The same geometry that shaped the galaxies also shaped the eyes that now study them, the hands that build telescopes, the minds that ask why. So when you look at the night sky and feel that strange ache of recognition, that quiet sense that you are both impossibly small and profoundly connected, it's because you are. You are built from the same curvature that shaped the stars. You are the bending that made the universe aware of itself. And in every heartbeat, in every flicker of thought, the cosmos continues its ancient curve, folding space into form and form into understanding. If the universe began with a single curve, an expansion from something infinitesimally small, then it's natural to wonder whether it might one day fold back in on itself. Whether the outward rush that began with the Big Bang could reverse, turning all motion inward again. Every galaxy that now races away might one day slow, pause, and drift homeward, drawn by the very gravity that once propelled it apart. This idea, known as the Big Crunch, imagines a universe not dying in stillness, but collapsing back into the same kind of impossibly dense curvature from which it began, an ending that mirrors its birth. If that were to happen, space itself would begin to contract. The great cosmic web of galaxies would start to tighten, its filaments coiling inward like strands of silk. The distances between galaxies would shrink. The light from distant stars would blue shift, growing hotter and brighter as everything rushed toward everything else. The night sky, which now expands into silence, would grow crowded again, filled with light, heat, and noise, as the fabric of reality gathered its energy for one final convergence. The universe would be returning to the same point of infinite curvature it once emerged from, a place where the laws of physics, time, and geometry cease to distinguish themselves. In that scenario, gravity would become the sculptor and the destroyer. Every atom, every planet, every star would feel its pull intensify. Black holes, those deep wells in the fabric of space, would swell as matter streamed into them, consuming the remnants of galaxies. Eventually, even the black holes would merge, their event horizons joining into a single, universal collapse. The entire cosmos would fall inward toward one ultimate singularity, the point where space-time bends so sharply that all paths, all motion, all possibility converge. But what happens beyond that curve? At the moment when curvature becomes infinite again, our equations break down there. Time itself, as we understand it, would stop. The distinction between before and after would dissolve, leaving only the geometry of compression, pure density, pure potential. Some physicists suggest that what we call a singularity is not truly an end, but a bridge. If space can bend endlessly, perhaps it can also twist, folding through itself like paper in higher dimensions. The Big Crunch could become the seed of another expansion, a new universe born from the collapse of the old, its laws and constants reshaped, its stars rewritten. If that is true, then the universe might breathe, not metaphorically, but literally. Expansion and contraction, outward and inward, a rhythm stretching across eons beyond count. Each cycle would erase the traces of the one before it, yet carry its memory in the curvature of its birth. Every atom, every vibration, every flash of consciousness could be part of a cosmic heartbeat that never truly ends. To live in such a universe would mean existing in a story without a final page, a continuum of creation folding upon itself, again and again, in endless renewal. Yet even if the universe does not end in a crunch, even if it expands forever into cold, thin silence, curvature remains at the heart of it all. Black holes already show us what infinite bending looks like, not on the scale of the whole cosmos, but in microcosm. Inside them, the curvature of space-time becomes so extreme that direction loses meaning. The boundary between inside and outside, between time and space, collapses. Everything that crosses the event horizon is carried toward a point that may not exist in any conventional sense, a singularity where our understanding fails. And still, those same black holes shape the galaxies around them, anchor stars in orbit, and generate the gravitational waves we now record as sound. Destruction and creation are not opposites in this geometry. They are phases of the same curve. When you imagine the universe folding inward, it's tempting to see it as a tragedy, an erasure of everything that ever was. But the universe doesn't fear its own endings. Curvature doesn't stop. It changes form. Even if everything we know were to be drawn back into a single point, that point would still contain everything, all the mass, all the energy, all the structure, compacted beyond measure. The same density that once exploded outward could ignite again, its potential released in a new expansion. Perhaps the Big Bang was not the first, nor the last, but simply one beat in an eternal rhythm of collapse and rebirth. And what, then, of beyond? If the universe folded entirely into itself, would there be anything left to observe, to remember, to exist outside the curve? The question may be meaningless. There is no outside to space, no stage on which it sits. The universe is self-contained, and so any folding it performs happens within its own boundaries, like thought turning inward. If there is something beyond, it may not be a place at all, but a different kind of being, a realm where geometry gives way to something we have no language for, a form of existence unmeasured by time, unbounded by light, unbroken by curvature. In the end, every theory, every model, every image we build of the universe's fate is a reflection of our own longing to understand beginnings and endings. But space itself does not think in such terms. It simply bends, evolves, and continues. If the universe does someday fold back into its origin, it won't be an ending but a return, the geometry of existence curving inward, gathering all its scattered pieces into one last, perfect shape. And from that infinite curvature, perhaps, another universe will unfold, carrying within it the quiet memory of all that came before.